Now that we've talked about this idea of Young's double slit and seen a little bit how the geometry works, I'm going to, again, kind of give you the sweetened condensed version, but we're going to talk a little bit about a diffraction grating. Effectively, what a diffraction grating is a whole bunch of slits. And we have our light source back here, so whether it's a candle or a light bulb. And we have light coming and hitting our diffraction grating. And we have some screen over here. And we know that for any pair of slits, we're going to get this pattern over here. But think of it this way: as we have more slits, the more selective our pattern is, in a sense. And so what we end up with is we still have the bright spot in the center, but now rather than having kind of these fatter lines, if I have more slits, my lines become more defined. Now, something that we didn't spend a whole lot of time mentioning before, but this idea that we said that we can represent d sine theta equals m lambda, or we can say dy over L equals m lambda. This was kind of wrapping up last time when we were dealing with a double slit. And we can still keep this, particularly here, with our diffraction grating. So again, a diffraction grating is just a whole lot of slits. Notice what is affecting my pattern here. So I can have my distance, L, affecting it. But really, in this case, with this diffraction grating, I'm not so interested in this distance versus the height. What I'm looking at is the wavelength. This is where diffraction gratings are particularly useful. Because notice that if I change, like for a given setup, if I have a given distance between my slits, okay, this is set, this is not changing in my system, and my sine theta bit here is kind of set in terms of my length. This y term can change. My mode, I can have different modes, different counters here. But if D and L are set, M is set. So if I change color, if I change wavelength, start thinking about those interchangeably. If I change wavelength, I'm changing color. So if I change the color of my light, I'm going to change where it hits my screen. So if I have white light here that's coming in and hitting my diffraction grating, what I end up seeing here is that I have red spots, or in this case, let's say I have my blue spots every so often. But then I also have, so my 0th order always has whatever color. But then I get my red that does something like that. And maybe I have, again, the center point collect any wavelength will hit at my 0th order. But then maybe I have some green in between here. And so effectively what I get then is a spray of color, but not just a random spray of color like it comes from the light bulb here. This is very specific because specific wavelengths are going to hit at specific heights, at specific angles. So diffraction gratings are really useful for something we call spectroscopy. Now remember, the spectrum, the electromagnetic spectrum, is all of the colors. So spectroscopy you can think of as measuring the color. You can actually put a number to it. That number is associated with the wavelength. So for spectroscopy, what you can have is a diffraction grating, and what it will do is it will divide up whatever light you send through the grating into its specific wavelengths. So usually with a spectrometer, what you're interested in is maybe just one of these. So maybe you have your diffraction grating, but then you have your camera that only takes up this much space, and this is what you're looking at. But the short of it is diffraction gratings are based on the similar principle of the double slit, where we're looking at interference from different slits. And we can get way deep into the geometry. If you want to do that, talk to me later. But the gist is that we can use this same relationship for our diffraction grating, and we can separate light into its different colors. And we can see what specific wavelengths are there, because different wavelengths, remember, are associated with different frequencies, which are then associated with different energies. So if we can specify our wavelength, that means we can get the frequency, we can get the energy. If we can get the energy, that tells us a lot about what element or material or molecule is present. Because this is the neat thing about light. Remember, we said it's a quantized energy packet. It has a very specific amount of energy. Think about something else that you've dealt with that has a very specific amount of energy. Electron orbitals have very specific amounts of energy. And depending on the element, you're going to have a different spacing between your orbitals. You're going to have a different energy between your orbitals. So if you have different energies, say you hit this atom with some light, and it pops, maybe it pops your electron up, but then that electron slams back down, it's going to have a very specific energy drop. In other words, it's going to have a very specific frequency that it emits, a very specific color that it emits. And so we can use spectroscopy to identify specific elements because of this progression here. We have specific energy amounts for specific elements, which then are going to produce specific colors that we can see when we use a spectrometer, a diffraction grating. So ultimately, that is a huge benefit and application of diffraction. Something else that I do want to kind of point out is that as you increase the number of slits, you're going to decrease your line width here. You're not going to have these big fat interference patterns. You're going to have really skinny, bright interference patterns. So a good diffraction grating will usually have hundreds of lines per millimeter. So we're looking at really, when we're dealing with visible light, what we need is something that has these slits that are on the order of magnitude of a wavelength of light, which incidentally is on the nanometer scale. So if we have several hundred nanometers, several thousand nanometers in terms of our slit width, that's going to give us diffraction. But if I have more slits, then what I end up with is, again, these tighter patterns that are more helpful for spectroscopy. So I've been throwing around this term diffraction without actually having defined it very well. We've said that light waves interfere, but what does it mean to diffract? Well, let's back up to a fellow by the name of Huygens. That's how we spell it. So Huygens noticed something about the behavior of light and of waves. Let's back up to our water wave example. So we have waves coming in like this, our plane waves coming in, and we hit the dam with some slit. And notice the slit is on the order of magnitude of the waves. It's not like my slit is huge and my waves look like this. Because in this case, I really am pretty much going to get the waves coming out like this, if this is my slit. And then if my slit is microscopic, I'm not going to see much of anything. I'm still going to basically block the waves. So I need my slit width to be on the order of magnitude, or near the order of magnitude of my actual wavelength that I'm dealing with. And what Huygens noticed was that we start to see this pattern. I can have a plane wave coming in, but it's going to put out a spherical wave. And he started thinking. And the way he started thinking about it was that every point on the wave is its own individual point of energy. And so we quit thinking about it in terms of one wave in a chunk, but we think about every point on the wave as being able to produce its own wave. And this is where Huygens' principle itself is actually a little more mathematically complex, but the short of it is each one of these individual points is producing a spherical wave, and it all cancels, and the next thing it produces is another, the total thing it produces is another plane wave. But what that means then is that at this point here with my slit, I have a bunch of individual points that are producing, each of them producing their own spherical wave. And when I don't have an infinite number of those, I don't get a nice plane wave front as my result. What I do start to see is this kind of curvature. So when we start talking about diffraction, diffraction is simply a fancy word for edge effects. So diffraction is how waves behave at edges. Now, this gets interesting when we start pairing diffraction with interference. So when we were dealing with our double slit experiment, we were really only looking at two sources and two waves, two spherical waves that interfere. So when we were dealing with our double slit pattern, I want to point out a few things. One is that our double slit pattern looked kind of like a cosine function. And we still had this bright center, but what we were looking at was this distance between the bright center and the next bright spot. This was our difference in spacing, the y we were looking at. What we're going to look at with a single slit is a little bit different. So again, we're looking at the edges. So I have my single slit, and with my double slit, with my diffraction grating, D is my slit spacing, so the distance from one edge to the next edge. So it's kind of like the spatial period of the slit. So from one point to the same point on the next slit, whether that's from bottom to bottom or top to top or middle to middle, doesn't matter. But with my single slit, I care about, we're going to call it A, my slit width. And similarly, I can have my screen over here. And if my wavelength is on the order of magnitude with the slit width, then I actually start to see this diffraction pattern start to form. Now, the reason we're interested in Huygens principle is because it means we have a whole bunch of dots that we can, I say dots, of point sources. We can treat the light coming in as an infinite number of point sources within the slit. What we're interested in, however, is pairs of point sources. So I'm going to draw a line down the middle of the slit, and I'm going to point out that we've got from this point to this point, we're looking at a spacing of A over 2. I have the same thing from this point to this point, looking at a spacing of A over 2. And the idea is that for every point above the line, I have some point A over 2, a distance of A over 2 below the line. So what I'm looking at effectively is a bunch of pairs. So I've got some distance here that I'm interested in, and the pattern that ends up forming when I have all of these pairs combining looks like something that we call a sinc function. And it's different because my double slit pattern, like I said, is more like a cosine function that kind of falls off at the edges a little bit. But this pattern is really bright in the middle, and then it gets dimmer and dimmer pretty quickly. And so what we're actually looking at here is from my center line, I'm going to draw a line to the first dark spot. So here, Y was from bright to bright. Here, Y is from bright to dark. So from rather from the center to dark. So this is Y1. This would be Y2, where these are just counters. If you want to use M here, M is just a counter. So this is the angle I'm interested in. And that angle, we can use the small angle approximation again. And we can say that sine of theta is approximately equal to tan of theta, which is equal to y over L. But then, just like we did with our double slit, we can look at these pairs. And effectively, what we're looking at is an optical path difference. So here we're looking at delta R equals, well, if I'm looking at a dark spot, I need to be destructively interfering. So remember, constructive interference happens when I'm offset by one wavelength. Destructive interference happens when I'm offset by half a wavelength. So where I have the dip, I have the hump, that sort of thing. So if I'm looking for my first dark spot, I'm looking at delta R equals some integer number of lambda over 2. So my first dark spot we'll say is lambda over 2. And again, if I'm drawing my triangle here, so just to kind of redraw a little bit, got my right angle here, some line theta. This distance is a over 2. This distance is lambda over 2. And so we end up being able to say, with our small angle approximation, sine of theta, so opposite over hypotenuse, looks like lambda over a. Well, when we were dealing with our double slit, we didn't have those factors of 2 in there, and it looked like lambda over d, but that was for a bright spot. Because we're only looking at a spacing of a over 2, it turns out we're still going to have this same ratio, this same relationship. And so what we can say is lambda over a equals y over L, or if we want to start talking about it in terms of this is m equals 1, this is m equals 2, so forth, so on, we can basically say, or let's go ahead and use P. Your book uses P. And this, again, P is just a counter, okay? Kind of like M has been a counter. So my first dark spot is P equals 1. My second dark spot is P equals 2. Okay. So I can take this relationship here and kind of summarize it or rewrite it. And what we end up with when we do that, we say A times sine of theta. P is my subscript, so if I'm looking at P equals 1, then it's just this angle. So this angle here would be theta 1. This angle up here would be theta 2 for P equals 1, P equals 2. Is equal to P times lambda. Again, this is just a counter term. So if I want to know where my first dark spot is, P just equals 1 here. If I want to know where my second dark spot is, I actually plug in 2 for P. And again, we just said that sine theta is equal to y over L if we use the small angle approximation. So we can also say that A y over L equals P times lambda. And at any rate, what this does is this allows us to form a relationship between my slit width and the spacing of my pattern. So if I have a greater width for a given wavelength, my spacing is going to be less. So let's kind of break down what we would expect to see. If I have a given length here, if my length isn't going to change and my slit isn't going to change, what happens if I change my wavelength? So if I keep these two things the same, if I increase my wavelength, I'm going to increase the spacing of my pattern. My Y1 is going to be greater. This pattern is going to be more spread out. So in other words, my longer wavelengths, like red, are going to be more spread out than my shorter wavelengths like blue or purple. Those are going to be more scrunched. Okay, that's one case. Again, if maybe I keep my wavelength set, so I'm just using one color, and I keep my length set. So if I want to change the width of my slit, so if I increase the width of my slit, I'm keeping these two things the same. So that means I have to compensate by decreasing my spacing here. So again, a wider slit is going to give me a more scrunched spacing on my pattern. Then it stands to reason that if I bring my length in closer, I expect to see that spacing get smaller and smaller and smaller. If I spread that screen out to where it's further down, I'm going to spread it out just because I have more room for my triangle to grow. Now, something that I hadn't mentioned is the shape of the slit so far. So what we've been looking at is this long rectangular slit for my double slit, or for my single slit, just one of them. But what if the shape of my aperture is what I'm calling whatever I'm shining the light through, is a circle? If I look at it from edge on, it still just looks like my single slit. So as it turns out, if I have a circle, the diffraction pattern that I get is really pretty similar to what I saw with my single slit. There is a slight difference. This is no longer a sync function. So for a single slit, we call this a sync function. This is what we call an airy disk. And it's just another type of function. But rather than being lines, what we see with the airy disk is actually a spot where it's bright in the center and then slightly dimmer as we go outwards, and dimmer and dimmer. So the airy disk is going to be how we define our diffraction pattern for a circular aperture. And I'm just going to go ahead and give you the equations because this is a higher function with the math. But what I want you to take away is that the width of my spot diameter here, so the width of this central bright region is going to be little w, and that is equal to 2.44 times L over D, where this is going to be L, and this is D. D is the diameter of my aperture. Now, where does this 2.44 come in? That comes specifically from this mathematical function. It's how it's called a Bessel function. And what we're looking at basically is from dark to dark, the width of that bright slit. And this is useful because when we start talking about the diffraction limitation of the eye, this is what we're referring to. So in other words, think of it this way. When you see a car coming at you when you're driving at night, the car is very far away and it looks like just one bright point. But as it gets closer and closer and closer, eventually you can resolve it into two headlights. So at what point can you resolve it from one headlight to telling that it's two? That's called your diffraction limitation. That's your resolution of your eye? Where does it go from being 1 to being distinguishable as 2? That's great for knowing about cameras. It's good for knowing about the optics of your eye. And it's related to this airy disk. In fact, just kind of a little free information for you. The way we define that is if these are my 2 airy disks, I say that I have reached the limit of my resolution when the peak of one disk of one headlight is at the 0 point of the other. This is the limit of my ability to resolve the 2 different headlights. So anyway, that's how we define it. This is kind of the limiting factor of us being able to tell that there are 2 different point sources. Okay, one more thing in talking about the wave nature of light, and that's something called thin film interference. And really, you can look in the book for all the specific equations. I want you to understand the idea behind thin film interference. Effectively, you've got light coming in, and where does thin film interference occur? Well, first of all, we need to define when thin film interference occurs. Well, it happens when there is a thin film on top of some other material. So, in other words, maybe like soap or oil or something on top of water, maybe. And we have air up here. Or maybe we have air, soap, air. But in essence, what we have is a thin film that has formed on top of another material. And we know from a very brief discussion that whenever we talk about light traveling into a different medium, it's going to slow down because of that absorption, re-emission bit. So the average speed of light is different. So we're looking at some index of refraction. So I'm going to call this index 1, this index 2, maybe this is index 3. And the idea, the short idea behind thin film interference is that we get some reflection every time we change medium. And so if light's coming in, we get a reflection coming back off of this surface. But we also have some transmission, some refraction going on. So we get that refraction, and if this width is such that I can set up a standing wave here. So remember when we were talking about waves, we could have any width of or any length of material, but we only got a standing wave when we were at specific lengths. So if we can get a nice perfect reflection that gives us something that spits back out something that actually destructively interferes with the original reflection. Let's see if we can. So if it comes back out such that these two waves destructively interfere, basically it cancels out a color. So I'm looking for destructive interference between my reflection from the first surface and my reflection from the second surface. And we have to have this secondary reflection or we can't have this interference going on. That's why it's called thin film interference, because I need a thin film of some other index here. I need a thin film of something so that we still get reflection off of it and transmission from it. So we get both of these rays. And when they destructively interfere, it blocks out a color. It cancels out a color. So a little bit about color. If you take, you can use red, green, and blue to create white light. If you don't believe me, very carefully put a drop of water on your cell phone screen and take a look at the different pixels and see where white light is actually formed from RGB. But if we want it, that's additive color. If we want to talk about subtractive color, if you take away one of those wavelengths, you're left with some combination. So if I have red, green, and blue, and I take away green, that leaves me with red and blue. That creates magenta. That leaves me with magenta. My CMY, well, for your printer ink, it's CMYK. So cyan, magenta, yellow, black. Cyan, magenta, and yellow are your subtractive colors. If you start with red, green, and blue and you take one of them away, you're left with either cyan, magenta, or yellow. So basically, those are three very specific colors, but this can happen for any wavelength of visible light. And when you take away one of those colors, you change from white light to something else. And so think about the colors you see in a soap film. So you see kind of that magenta or that yellow or that kind of cyan blue. And that's what you're seeing when you get a thin film. Now, if you see a change in color, that's because you're seeing a change in thickness in the film. So different wavelengths are canceling. That's the idea. So some wavelengths at this thickness are going to reflect back perfectly and give me destructive interference, but the other wavelengths not so much. If I change my thickness, that means a different wavelength for a different thickness can give me that destructive interference. So I change color as I change thickness. Like I said, the equations that you need for all of this are in your book, but I just want you to have a basic understanding conceptually of what we're talking about when we're dealing with thin film interference.